All right, class. Today we're going to look at calculating average masses of isotopes and electron configuration. You can find this in Chapter 1. Okay, so you should see this slide posted for Chapter 1 and calculating atomic masses of isotopes. So if you ever wondered when you look at the periodic table, you might see carbon, as I typically use. And you might see like 12.01 and some digits. But whenever I talked about the isotope notation, you might see carbon 12 or carbon 13 or carbon 14. And you may wonder, why is there a decimal point right here? And the reason is that number is the average mass of all the isotopes while taking into account the natural abundance of each isotope. So a good example is seen in this slide right here. You may notice boron on the periodic table. Below it has a mass of about 10.8 units. Now, where did that number come from? I'm going to show you how to calculate this, and this may be important for a test. So, in order to solve this problem, I'd have to give you some information. I'd have to tell you, number one, which mass number boron is, and the relative abundance of each isotope. Okay, and so you may notice that boron 10 is the minor isotope. It only exists in 19.9% of nature, whereas boron 11 is 80.1%. Okay, now let's act like you didn't already see the answer here. What you're going to do first is you're going to take that 19.9% and convert that to a number. Okay, that's not a percentage, just a regular number. So divide by 100 to get 0.199. Okay. And what we're going to do is take that and we're going to multiply it times 10. And what you should get is 1.99. Next, we're going to do the exact same thing for the other isotope of boron, which says it's 80.1%. We're going to divide that by 100, which should get you 0.801. And now we're going to multiply that times 11. Okay. 0.801 times 11 will give you 8.811. And all you do now is add those two numbers together. You should get 10.801 equals 10.8. And so that's where those numbers come from. The scientists have taken into account all the natural abundances of the isotopes that are seen in nature. Then they average them together, practically using this exact method, okay? And so practice this and get good at it. Just remember, take that percentage, it has to be given to you, and divide by 100 to get to the number, not the percentage, and then just multiply it times the mass number, and then add the two together. Now we're going to talk about quantum mechanics and valence electrons, okay? So, quantum mechanics is a modern theory that states the following. Energy is quantized. Electrons are organized according to their energies into sets called shells. The shells are further divided into subshells. And the subshells of each are labeled in order with letters such as S, P, D, and F. Okay, the different subshells hold a different maximum number of electrons. For instance, any S can hold up to 2 electrons, P 6, D10, and F14. Though usually, especially in this class, we don't deal too much with the F subshells, okay? And so what you're going to see is things like this: 1s2, 2s2, 2p6, and things like that. And so just to highlight what these things are, these numbers right there are the shells, okay? And so shell 1, and then a subshell of that is indicated right here with the S and the P. And then these numbers right here are indicating how many electrons are in each shell. And so in each subshell. And so in the 1s subshell, there's 2 electrons. In the 2s subshell, there's 2 electrons. In the 2p subshell, there's 6 electrons, okay? And I'll try to explain it better as we go on. But first, you need to figure out what these S, P, D, and F subshells even are. And so I'm going to do my best to explain that in this next slide. So why don't you go ahead and print out and get your periodic table. It should look like this as it's posted online. This is the periodic table that is approved by your instructor to be used on the exam. Now keep in mind you're not allowed to mark on this for your exam, but this is the periodic table we recommend using on exams and quizzes. You'll find one of these posted in Unit 3, Unit 6, Unit 8, Unit 11, and Unit 15. Okay, so if you just forget where to find these in your course, that's where they are posted. It's the same one every time, but just try to organize this in a location to where you can find it. But anyways, as you look at your periodic table, you're going to notice that this is going to be your S level right here and right here, but then your first two columns on your periodic table are also going to be S's. Over here, with the exception of helium, those are going to be your P's. Remember, this is actually helium. If you actually want to take that to a periodic table, your transition metals right here are going to be your D subshells, and then your F's are going to be your lanthanides and actinides. And so what does that look like on an actual periodic table? Well, all of these are S, and helium's also an S. And then you have your P's. Remember, it goes from about right here. Those are your P's. You may recall D's are right here. And then your F's are down here, your lanthanides and your actinides. So those are subshells, you may recall. So let's figure out how to do this. This is going to be called your electron configuration, and by just looking at the electron configuration, you're going to be able to know the exact identity of the atom or element on the periodic table of which we're talking about. Okay, so think of it kind of like an address for a house. Okay, if you said you lived at 245 Cashew Court, that tells you a location. If you said that's in Houston, Texas, that gives you more information, and that's what we're doing. We're identifying an element based on the electron configuration, meaning just how the electrons are organized around the nucleus. Okay, so here's how we're going to do this. It's going to be a shorthand notation. I kind of gave you a hint as to what it looks like earlier. And it follows the trend of the periodic table going from left to right. And the total number of electrons in your configuration should equal the total number of electrons for that atom, assuming it's neutral. At least for this class, that's the easiest way to do this. And so you can add the electrons per subshell to get the total number of electrons for that particular shell. So let's see what we're looking at. So write the electron configuration of the following neutral atoms. And so hydrogen. Let's go up and look at hydrogen on the periodic table. I'm going to highlight it for you. There it is right there. And notice that hydrogen is in S subshell, and it has an a 1 for the shell number, okay? So remember, this would be 1, 2, 3, 4, 5, 6, 7, okay? So the way we're going to write this is pretty simple. Hydrogen is one of the easiest ones. It's simply on the 1s, and because it only has one electron right there, it's just going to be 1s1. And does that make sense? Hydrogen has one proton, therefore if it's neutral, it should have one electron. And you notice right here, that indicates that it only has one electron. It's located in the first shell in the S subshell, okay? Subshells can be a little bit tricky. They each take on a particular shape. S is a ball. P usually is this dumbbell shape. And D just gets a little more tricky, and F is incredibly tricky. But they take on particular shapes, and we're not going to get too much into that, okay? Let's take a look at aluminum. What we're going to do now is we're going to find aluminum. There it is. It's number 13. And notice to get to aluminum, you have to travel through the 1s and get your 2 electrons, 1 and 2. Then you have to travel through the 2s, get your 2 electrons, travel through your 2p, get your 6, travel through your 3s, get your 2 electrons, and then you wind up there at a 3p and 1 electron. So if you have your periodic table nearby, you may be able to see this. It's 1s, and then you take up those 2 electrons because you went through helium. And then next you're going to go to the 2s, there's 2 electrons. And then we go to the 2p, and you fill that one, 6. Then you go to the 3s, 2, and then it's a 3p, 1. And then you know you did it right if it totals the number, the atomic number, right? So we have 2, 4, 10, 11, 12, 13. And that's exactly what aluminum is, okay? Now, I want to show you a trick, but it may have to be posted. And the trick is this. Okay. And then if you were looking for aluminum, the way you do this is you travel down there. Like that. And then notice that what we did is we stopped